Um, so today we're going to go through the formal definition of the integral, and that's the process of finding the sum underneath the curve. So last time, what we did was we look at a graph. We look at a graph, and my graph will look something like this. We have the x and the y axis, and we're going to have a curve, something that look like that. And we're going to try to find the area underneath the curve from A to B. And we went through the whole exercise of finding the area underneath, and we discussed that the best way to calculate this area is by breaking this area down into little rectangles. So here, this part refers to the rectangle. This is the width, right? And this is the height. This is the height of the rectangle. So this is how tall the rectangle is. This is how wide the rectangle is. And this part here is the sum. This part tells us for all of these rectangles, we're going to add them up. The area of the rectangle, we're going to add them up. And then the limit says we're going to make as many rectangles as we can. We're going to try to fit as many rectangles as we can in there. And that is going to be the area. Instead of writing it like this, we're going to write it using a different method. We're going to write it like that. So this is the integral form of finding the area. So we're going to write, we're going to represent it with that. So you notice as we read through the instruction, we are having a function between A and B, right, over this interval. And we actually have a process, right? We first divide it into n little rectangles, and this is my width. And then we try to find some endpoints on the intervals. And we try to, pick a point in these little intervals. And it turns out it doesn't matter where we pick. And so it turns out it doesn't matter where the sample point is. This is called the integral, the definite integral from A to B. And this is what we use to represent the area. So just like before in differentiation, we have a curve, right? And then we sort of discussed that if I have a curve like that, if I pick a point, and then I try to find the slope of the tangent line, we say that the slope of the tangent line here is, you can write it as df dx, okay? We can write it as that. Or we can write it as f prime, right? We can write it as f prime. This is the same idea. The only difference here is that my function has two different part of this. So there are two different part of this symbol. There's the integral sign on the left, and then there's the independent variable, kind of like the width, that's written on the right-hand side. So the difference here is that the symbol have two parts to it, on the left and on the right, and they're together. And it's really common, and I can tell you, it's really common to forget to write the dx. Because normally we'll start and we'll be like, I completely forgot writing, I completely forget about writing the dx part. Because we're so used to writing the symbol in the front, and it's hard sometimes to remember that we need something at the back. Okay, if we can find the limit, if we can do the calculation of the area, then we can say that the function is integrable. Just like we can say a function is differentiable when I can find the slope of the tangent line. If I can find the area, we say that it's integrable. The word definite here means that we can find a value. It means that we know the beginning, we know the end, and we can calculate the value of the area. a few words about the symbol. This curvy part up here is known as the integral sign. So it's like a little s because we are trying to add up all the little rectangle. So this little curvy s is the integral sign. The function inside is called the integrand. We don't really, yeah, you'll see these phrases being used in the textbook a lot. A and B are called the limits of the integration. This tells you where we begin and tells you where we end when we draw our area. A is the lower limit, B is the upper limit. And the dx here really just tells you that the variable for the horizontal axis, the independent variable is x. And of course, this process of finding the area by calculating the integral, that's called integration. It turns out it doesn't matter whether I'm using x or t or r. And what I mean by that is this. When you go through differentiation, you'll notice that if I do d dx, and then I write sine x, this says that, oh, we have a function sine x. Let's find the derivative, and the derivative of sine is cos x. Yeah. So we still need to remember these. Okay? We still need to use this. If there's one thing that you need from your calculus 1, from your differentiation class, is that you need to know the derivative of these basic functions. Now, if I do the same thing, but with a different variable t, and if I have a sine function that uses the variable t, then the whole process hasn't changed. Then the derivative is cosine t. Right? This statement here with the integrals means the same thing. If I have a function of x, and I'm telling you x is the variable that we are doing the integration with respect to, then we're going to have the same answer as if I replace all the x with t. So if I replace all the x with t's, we're going to have the same answer. This sum, where I add up all the rectangles before I do the limit, this is called the Riemann sum. So sometimes a lot of the textbook will start with Riemann sum as your first class. Okay. By the end of today, all we are expecting you to do is to be able to know some basic idea about the area under the curve. So we'll sort of show you this. What we are expecting you to understand at the end of today is to know that when I find the integral, when I try to find this, and if I tell you A is here, B is here, what we are doing is we're finding the area between my curve and the x-axis. We're trying to find the area here. And then there's one more thing. If we're below the x-axis, it's a negative number. This is going to be a negative number. So if I tell you that the area here, the area A1, so the area here is 3. Let's say the area for the second piece, A2, is 5. Sorry. And let's say this piece is 2. All right, A3 is 2. What we expect you to understand is that if I ask you to find out what the integral is, the integral in this case will be 3 minus 5. Why do I use minus? When your graph is below the x-axis, then of course, if you think about your rectangle, right? If you think about your rectangle that you're drawing, this rectangle, the height would be a negative number, right? The height might be like -2. So if I calculate the area, width times height, width times -2, it's going to give me a negative area. So when we have, when the function goes below the x-axis, becomes negative, the area is going to be negative. And we're going to plus 2 here for the end. And then this integral in this particular case will have a value of 0. All right, so we want you to be able to visualize and understand the basic kind of like the graphical meaning of the integral. And we also want you to be able to calculate the Riemann sum. We want you to be able to calculate the Riemann sum and hopefully be able to use the definition. In Riemann sum, when I just have the summation symbol, that means I'm breaking the curve into these little rectangles. Now, this is the case where I am not doing the right endpoint or the left endpoint, because you'll notice that where the graph is, where the height is, see, if you look at the height over here, this is more like in the middle. Okay, so we're sampling in the middle, but it doesn't, yeah, so we'll tell you how we sample. In this particular example here, we're sampling on the right-hand side. And of course, the relationship between these two, between the limit, between the Riemann sum and the actual integral, is we have to do the limit as n approaches infinity, right? As the number of rectangle becomes very large, as I use an infinite number of rectangle to calculate the area. We're not going to hopefully spend too much time on the Riemann sum. So we're going to quickly walk you through the process. When I break it down into 6 subintervals, we want to say that the total interval is from 0 to 3. The width is 3. I'm going to cut them into 6 little rectangles. And each of these rectangles will have a width of 1/2. 3 divided by 6. Because I'm using the right endpoint, I'm not going to use 0 because 0 is on the left-hand side. So the first rectangle, we will use 0.5. And then we'll go up by half, 1, 1.5, 2, 2.5, 3. So we're going to use that. What you can see is, you can see over here, we are using 0.5. And we're using the y value for 0.5 for the first rectangle, For the second rectangle, we're going to use 1, and then 1.5, and then 2, and then 2.5, and then finally at 3 for the last rectangle. Now, of course, how did I calculate the value? Now, remember, we had to go back and look at my function. My function is x cubed minus 6x. So my function is x cubed. Remember, the function is x cubed minus 6x. So when f is equal to 1, it's going to be 1 minus 1 minus 6, 6 times 1. So that's why we have f of 1 is -5. Okay, so we calculate them like that. F of 2, if I put 2 in, 2, 4, 8, 8 minus 12, minus 4. Okay, so that's where these numbers come from. F of 3, 3, 9, 27, 27 minus 18, so plus 9. Now, of course, these are the y values. We're going to take the x value. We're going to find the x value, find the width. And we already know what the width is. The width is 1/2. And since everybody has the width, we're going to factor it out in the front. And so that's how we normally do the Riemann sum to simplify. We'll factor out the width and we'll put it in front. Here we skip a whole bunch of steps on the in the textbook example. And what you'll notice is that at the end we get a negative number. And this sort of tells you, right, why the very first the second rectangle here, the one in blue, the one that's circled in blue, it's a negative number because the y value here is -5. Right? So when I multiply -5 by the width, I'm going to get a negative number. So anything that goes below the axis is negative. So you notice over here, negative for the one at, oh, wrong color. Okay, and then red here, go up. This is 9, right? This the height over here is 9. Okay, so I hope this helps you visualize what is happening here. Okay, so this is how we calculate the Riemann sum. If we were to ask you a question to calculate, to approximate the area, this is the type of questions that we will give you. Okay, something very straightforward. You just plug it in, use the summation part from the definition. But today I want to emphasize positive and negative results. Now, if you want to take a screenshot, you can do that before I move on. The next example that we will do, we will go a step further and we are going to show you how to go. We're going to quickly review how to go from Riemann sum to the actual area, to the actual integral. So integral means the exact area, just like derivative means the slope of the tangent line. So first, a little bit of background. So if I have a continuous function, so just like when I do derivative, we need to have like a continuous function before I can find the derivative, because we need to calculate the slope and make it closer, make the second point closer and closer, and make that distance 0. So if we have a continuous function, or if we just have a few jumps, then we can manage that. We can find the area underneath. Then we say that then we can say that it's integrable and we can find the integral. Now, it doesn't matter whether I choose the left endpoints or the right endpoints or anywhere in the middle. When we do the limit, because the rectangle becomes super small, it does not matter whether we pick the right-hand side or left-hand side. We're always going to have the same result. So over here, we're going to always use the right endpoint to make things a little bit easier. So the difference between what you see here, the difference between what you see in this theorem over here versus what we talk about at the beginning, at the beginning we said it can be any point. It can be the right-hand side, left-hand side, middle, or if you want, you can go right-hand side and then left-hand side and then right-hand side in the middle. You can do whatever you want. But here in this theorem, we're trying to say that let's always pick the right-hand side to make things easier. Because if I always pick the right-hand side, all the x's that I'm going to test are going to look like this. I'm going to start from where the interval starts, 0. Then the first point will be 1 times times half, 1 times half. The second point will be 2 times half. The third one will be 3 times half, 4 times half, 5 times half, and 6 times half. Half is the width in this case. So this is what we're going to do. We're going to do 1, 2, 3, 4, 5, multiply by the width. And if we don't start with 0, we have to add the starting point. So that's the only difference in the theorem that relates the Riemann sum, the limit of the Riemann sum to the integral. Okay, we will come back and use this page for a second. So when we ask you to find, the integral using the definition, I'm going to have to figure out whether I want you to do that on the test or not, because it's a long question. We might do one, but with a very simple, just x or just x squared or just x cubed, something very straightforward. The process is this. First, look at the limit. So this tells me, oh, by the way, in case you're wondering what this is, notice how it's the same x cubed minus 6x from 0 to 3. So we are doing, I don't know if you know this, we are doing the same function with the same right-hand side and left-hand side with the same interval, but we're not cutting it into 6 rectangles. We're not cutting it into 6 rectangles. We are, in this case, going to cut into n rectangles and making n as big as we can. That's what we are doing. So if you look carefully here, the first step, we're going to have something very similar, but instead of 6 rectangles and do 3 divided by 6, we're going to have 3 divided by n. Instead of being able to label all the points, like half and 1 and 1.5 and 2 and 2.5, we are only able to take the 3 over n. That's the width. And of course, the first point is at 1 times 3 over n. The second point is at 2 times 3 over n. The third one is at 3 times 3 over n. I is my counter. I is the ith point. I don't have to add in this case. Because 0 is this 0 here. So I don't have to add anything. If I start at 5, then every number that we find has to be added onto 5. Okay. And then the difficult part is, of course, calculating the area of the rectangle. So here we're going to calculate the area by doing the width. Oops, wrong color. We're going to take the width. And of course, the width is this 3 over n, right? We talk about the width. We use width 3 over n like that. The height is the y value. And what we're going to do is we're going to take, hold on. Remember, this is the x, right? So this part over here is x. But we write xi because it can be the first x value, the second point, the second the first point, the second point, the third point, the fourth point, all these different points, because we're dividing the rectangle, we're dividing my interval up into n rectangles. So we're going to call each of the right endpoint, point number 1, point number 2, point number 3, point number 4, all the way up to point number n. So we're going to use this little subscript. Each of the point has this x value. Right, so this represents like the 0.5, the 1, the 1.5 from before. So the purple thing here represent these values. And of course, we don't use these values right away. We have to put it into our function, right? We have to put them into our function. So we're going to put our y value into the function. We're going to put our y value into the function. So we're going to take these and we're going to put them in here, into my function. Right? I'm going to put them into my function. And what will it look like? It will now look like this. Right? This is the y value. So this is the whole thing. We have x to the power of 3 minus 6x. But my x is going to be all sorts of numbers that is going to be changed. The width, we are going to pull it out. So you notice the width is now pulled out. So over here, we're using a special algebra technique. And the technique is kind of like this. Let's see if I need to go back to the previous page. So one of the properties, I apologize for the ugly thing here. It's better if I don't erase it. So what we are going to focus on is one special property over here. You'll notice how we have this special properties here. This says if I am multiplying a number onto every single term. So let's say instead of adding 1 plus 2 plus 3 plus 4. Okay, hold on. If I'm doing this, if I am. So I'll quickly explain to you what this means. If I'm doing 1 plus 2 plus 3 plus 4 plus 5. This, we will normally write it as a sum. We'll say we start from 1. We go all the way up to 5. And we're just going to add our number I. We're going to add our 1, 2, 3, 4, 5, and we're going to add them together. If I have the square here, 1 square plus 2 square plus 3 square. So if I have something like that, if I have the square here, this means I have 1 plus 9 plus, 1 plus 4 plus 9 plus 16 plus 25. What we are trying to sort of tell you is that we can solve the answer using this equation. And what we can do is instead of writing it like this, n is 5, I can write the result as 5. 5 plus 1, that's 6. 2 times 5 plus 1, so that's 11 over 6. So what you notice is that this part and that part goes away. We have 5 times 11. It's just 1 here. 5 times 11, the answer is 55. Okay. So that's what the answer, that's what this thing is. This helped me calculate the result easier. Okay, instead of adding every single term. Now you'll notice in this particular case, if I add every single term, it's not too bad. So because I have 25, 25, 50, 55. Yeah, so I can do that. But if you add it all the way up to 100, or in the case infinity, then we wouldn't be able to. Then we would need to have some formula. Now this purple rule over here says this. If I have something else, that look like this, equal to, instead of, let's say I have 2 plus 8 plus 18 plus 32 plus 50. Instead of something that look like the top one, if I have the bottom one, I have everything that is the same but multiplied by 2. Okay, so that's what we have here, right? We have a sum. We have I equal to 1, 2 times I squared, and then 5. What this rule tells us is that the answer is really the same thing as, because every term has a 2 in it, we can factor it out to the front. We can factor out the 2. So I can say, I can factor out the 2, and then I will take 2 multiplied by whatever the end result is inside. So I can say 2 times And 1 plus 4 plus 9 plus 16 plus 25. So I'm going to pull the 2 out in front. And that basically means 2 times this 1 plus 4 plus 9 plus 16 plus 25. Right, and of course you'll look at this and be like, that makes sense, right? I factor out the 2. So my answer is now 2 times 55, 110. So we have one special rule that look like this. So that's the special algebraic rule that you see here. Okay, and now we need that algebraic rule because you'll notice that n3 over n, it's a fixed number, right? It's a fixed number. If I say there are 6 rectangles, if there are 6 rectangles, the width is always going to be 1/2, always. So I'm going to be able to factor that out in the front. It's a constant. It doesn't change. Whether it's the first term, second term, third term, fourth term, fifth term. Remember, our width is always 1/2, and we pull it out to the front. So we can do the same thing here. The only thing we have to keep inside is the part that has the I in it. Because the first point will have a different value as the second point and the third point and the fourth point, because the Y value of those will be different. Because they have I inside. Anything without I, we can pull them out, factor it out. Once we factor it out, okay. So that's sort of where this story comes from. Okay, so that's where this part looks like. If you want to take a screenshot, you can do that. If not, we'll keep going. Okay, so the next part here is a little bit messy. Once we have that, okay, we need a few more rules to simplify this. But first, we can cube this, right? And multiply 18 in. So I multiply 18 in, and I cube every single term. I get 27 I cube n cube. We can continue with pulling things out in the front, because in the end, we really only need to keep I behind, right? The 27 is just a number multiplied by it. I can pull it out to the front. So I can pull out the 27 to the front. I can pull out the n cube to the front. And the only thing I will have left is I cube. Same thing with the back. We're going to pull out the 18. 18 times 3 is 54. We're going to pull out an extra n, so we have n squared. We are left with I. When we're adding up two different parts that's subtracting each other, I can do them separately. I can do the two sums separately, subtracting each other. You'll notice these rules are very common. We do similar things in derivative. We do similar things in all sorts of algebra. So these are algebraic properties that we commonly see. You'll notice we do the -1 like that. Okay, so if I have a term, say if I'm subtracting 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4 plus 5, minus the square, 1 plus 4 plus 9 plus 16 plus 25. Right, if I need to subtract them directly, if I do 1 minus 1, 2 minus 2 square, 3 minus 3 square, 4 minus 4 square, 5 minus 5 square. It's the same thing as doing all the 1, 2, 3, 4, 5 added up together, then add up the 1 square, 2 square, 3 square, 4 square, 5 square, and then subtracting the squares. So they're just different order. We can do the same thing here, separate them into different order. And the goal of doing all these ugly things is eventually get to this, a sum with only I inside. Here we have an I cube term. Here we have I. Then we go back and look at my formula. Okay, so if we ever needed this, the sum of the powers, these ones will be provided to you on the test if you need it. I'll put them right underneath the question if you need it. These ones you have to know. These are kind of properties of the sum. These are kind of like the distributive properties, the summative properties. Yeah. The additive properties. So they're pretty common. So these ones we're not going to give you. But you were supposed but if you need any of these ones up here, we'll show you. Here we have the I with the n and n plus 1 over 2. And then we have the I cubed with the square here. So you notice we have the square. And then we have the n plus 1 over 2. Right, and if you think about it, it's kind of cool. It's the sum of the cubes are sum of the values themselves, but cubed, but squared. What we are going to do, if you look at the algebra here, we put the n to the power 4 inside, and we pull the 2 square outside. So the 2 square comes out, becomes the 4 underneath. The n to the power 4 goes in, but because I have a square, it's really n squared inside. And then I divide one of the n here, and then I take another n and I divide it into this term to get 1 plus 1 over n. Right, so if you're not sure, you can write it out. Right, so if you're not sure, write it out. So the whole thing will have n, right, n plus 1, and then another n plus 1. Right, and then we're going to divide it by n to the power of 4, right? So we're going to have this, and we're going to divide it by, this is of course the square, and we're going to divide it by n to the power of 4. And so we're going to divide it by n here, n here, n here, n here. We're going to cross out 2 of them. And for this one, n plus 1 over n over n is 1, 1 over n is 1 over n. Okay, so that's how we got that. Same thing on the back. Once we have limit approaches infinity, anything with n in the denominator becomes 0. So this becomes 0, this becomes 0. So we end up having 81 over 4 times 1 minus 27. And whew, we're done. We went through all this really annoying process to eventually find the answer. What we are going to teach you next Tuesday is the following. Since we're here, since we went through all that trouble to calculate this result, you might ask me a question. At this point, you should ask a question. Are there an easier way to do this? Are there an easier way to do this? And the answer is yes, there's an easier way to do this. And so this, you only see it at the very beginning. You see it in the first 2 classes. But are there easier way to do this? And the answer is yes. If we look at this function, and the reason why we teach you derivative first is because integral is the reverse of differentiation. So if you think about which function gives you the derivative to be that, so what's the antiderivative of this thing? You'll notice that the antiderivative of this function is antiderivative x to the power of 4, right? If you take the derivative, you will have 4x cubed. So you have x cubed. And then we have 1/4. If you look at this function, the derivative is 4 times a quarter, which goes away, x to the power 6. Second part, the antiderivative, I need one higher power, so x squared. And of course, we'll show you a little bit more. We'll show you a little bit more steps later on. So today, I just want you to discover the rules. So here we have x squared here. And if I have x squared, that doesn't give us 6x. So we'll need 3 in the front. Okay, we'll show you some more proper steps later on. But for today, we want to show you that this function, if you take the derivative of this, so if this is f prime would be that guy, right? That would be f prime. Yeah. Okay, and now some fancy thing. Now, what we want to do is we want to ask you, what's this function when x is equal to 0? So normally when x is equal to 0, and what's this function when x is equal to 3? Now, what you'll notice is that when x is equal to 0, the whole thing is 0, right? When I have x equal to 0, the whole thing is 0. When x is equal to 3, let's use a different color. When x is equal to 3, if I put it in, you'll notice that I have 3 to the power of 4. 1/4 times that minus 3 times 3 squared. Okay. And what we need to do is we need to actually take this value minus the green result. All right, so we actually need to take this, and then we are going to minus the 0. Okay, so that's the proper way of doing it. We'll tell you why that is later on, and we'll give you a little bit more rules that you can follow on the book. But right now, what I want you to notice is this. Hey, isn't that the answer down here? Right? That's the answer. We didn't have to do all these crazy things. So we'll go through this step next Tuesday. And from next Tuesday on, from next Tuesday on, besides possibly the tests and the assignments, we will never have to do this again. Right? Eventually, we're going to show you rules that sort of do the antiderivative, right? So the gist of the rule is we're going to do the backwards of a derivative, and that magical function that we just found happened to be the area. Okay. And so that's the cool thing. That's why integration and differentiation are very similar to each other, and it would help you greatly if you remember all the differentiation rules. If you don't, it's still possible. You can still do fine, but it's nice if you can connect the two. Okay, if you need to take a screenshot, you can do that now. If not, we'll continue. Okay, now is actually a good time to take a break. So let's take a 5-minute break. After we review the definition using the limits of Riemann sum, there are a few things that we are starting to notice. One of the things is that if I do my limits of integration differently, so you notice before we did something like from 0 to 3, right? We did something from 0 to 3. And of course, the width of this interval is 3, and then we use that to divide by n. Now, if I flip them around, if I say 3 all the way up to 0, we can do that. It's okay to do that. But if I do it from 3 to 0, the interval is now -3. Because we're kind of going backwards, right? We're going from 3 going backwards to 0. So each of the width is now going to be negative. When I do the width will now be 0 minus 3 divided by n. So it will be a negative value, -3 over n. Because of that, the integral will be negative. So if I reverse the limits, the area that we calculated, because we're doing this backwards, we're going to have the negative value of what we have. So that's the first property. So that's the first thing that you'll notice from here, straight from the definition. And the second definition is that if these two numbers are the same, if I say, let's integrate it from 3 to 3. And if you look at the graph, it would not make a lot of sense because you're saying, let's look at 3. And then we're going to look at 3 again. And let's find the area underneath. And you will say to yourself, well, there's no interval, right? The interval is 0. Delta x is 0. So when delta x is 0, then when the width is 0, the area is 0. So that's why the whole value of the integral, the area will be equal to 0. So this is why we have to go through Riemann sums first before these rules, these properties becomes really obvious. We have to go through the definition. Just like when we have derivative rules, we go through the definition. Then we have a list over here. This list should look familiar, right? Because if I have 3x squared as my function, let's say my y is equal to 3x squared, and y prime, right? We would our power rule only works with x to the power of something. So we tell you that the 3 doesn't do anything. 3 stays in front, and then the back we continue with what a normal power rule is with the 2x. So these rules are a little bit like that. Specifically, this one is that one. This one is very similar to this one. They're cousins of each other. So over here, this tells us if I have a constant in front of a function, I can just ignore that constant, pull it out to the front, just like when I do derivative. And then I can do the derivative the same way that I would do with any other function. So earlier when we talk about 1 to 5 x 2x dx, we can totally say that, hey, let's just do 1 to 5 with x and then dx like that. Right, and with x, you notice that you have a little rectangle going from 1 to 5, and then here the height is 4, so you will have a different number. In this case, 12. 12 times 2 is 24. So you have the same answer. So you can go through the same process. You'll notice, and of course, we know these rules, not because we hand wave it. It's because if we rewrite them as a Riemann sum, if I write it as the limit of the sum of my function CF and then multiply by delta x, you'll notice that we can pull the C all the way out to the front, and that's how we can do this. Same thing with the additive rules and the subtractive rules. These two over here are very similar to the rules that we use in when I say, let's say y is equal to x cubed minus sine x, right? Then we would say y prime is equal to, I would do this part first, right? And then I would do the second part separately, and I would just put a little minus here. So I would do 3x squared, and then I would do cosine x, and we would just minus that. We would subtract it. So now what we are going to do in integral is the same. If I'm integrating 3x squared minus cosine x dx, we're going to tell you that this is the same as breaking them up separately, 3x squared dx. So we're doing 3x squared first, and then we're going to do minus. We're going to have minus here to have the correct sign. And we're going to have cos x here. And right now we are stuck over here. Okay, right now we're stuck over here. But if you remember the little preview that we talk about using the relationship between derivative and integrals, you'll notice that if this is the derivative and then I'm trying to integrate the derivative, that gives us the original antiderivative function. So this is going to give us x cubed minus sine x. And then in these cases, we have to do a plus c, but we can talk about that later. So right now, you don't have to know what the answer is. You will have to know at least the beginning part next week. But for now, you don't have to worry too much. And what you'll notice is that in this case, at least going from this step, today we're just learning what to do to go from this step to that step. And that's using property number 4. We can subtract them separately, separate them, just like how we have, just like how we do the derivatives. The last thing to remind you is this. For all of these rules, we can always think about the picture, the pictorial, the graphical meaning of the integral. So if I have a constant c, so c is a number, c could be like 3. And so the height is always 3. Then, of course, the integral, the area is the distance here, is the distance here. This is, of course, b minus a. That's the distance here. And then the height is 3. And of course, the area of this rectangle is 3 times b minus a. So that's why it's c times b minus a. That's where this comes from. So we actually, if we evaluated the result. So when you have a constant, that's the answer. So right now, if I say 1, 2, 4, 3 dx, we now know what the value, we know what the number is. It's 3, that's the height, multiplied by the width is 4 minus 1. Right, the width is 4 minus 1. And this is going to be equal to 3 times 3, 9. And so after today, you are able to do this. And of course, we know what happens if I do 1 to 1 and then 3 dx. You don't even need any calculation. We can put it into the calculator, but this is going to be 0 because these two are the same. And of course, I can do 4 to 1. From 4 to 1, 3 dx. And we can use the formula blindly if we want, but we can also remember that it's just the negative version of that. That's going to be -9. So that's the first 4 rules. And we'll use these every day. And we'll use it so often that we forget that we talk about it. And of course, these come from the definition. If you want, you can take a screenshot before we move on to the next slide. We'll give you a couple of examples. Here, we're going to evaluate something more complicated, and we're going to use some value that we know already. And because this is a sum of 2 different terms, we can break it up, right? We can take this integral, we can break it up. We can do the 4 first, then we can do the 3x squared. We know how to do 4. That's a height of 4 multiplied by a width of 1. 4 times 1 is 4. For the other part, you'll notice that it starts to look like the part that's given. We have the 3 as a constant in front. Let's pull the 3 out. Now we can find the integral here. And we know what the value is. The value is 1/3. So we're going to put 1/3 here. 3 times 1/3 is 1. So I know this whole thing is 5. Yeah, so it's kind of cool. Once we can break things down, we make things a lot easier. There are a few more. There are a few more rules. We're not going to use these ones as often. Number 5 is easy to understand. If I integrate from A to C, that means I'm finding the area of the first part. If I add it to the integral from C to B, that means I'm finding the area underneath here from C to B, the second part on the right. That's of course the area going from A all the way to B, so I can add them up. Provided that it's the same function. So the function has to be the same inside. So these ones here, we only use them in the future with proofs, and we don't use them as often as the first 4. Over here, it says that if my function is bigger than 0, so if my graph is always on the top, then my area is going to be positive, right? That's what number 6 says. If my function is positive, then the area underneath here is going to be positive. The next part here says, if I have a function that's always bigger than the other function, right? So if I have a function up here, that's f, and if I have g, so let's say if I have g, g can be like that, that's g of x. So you notice f of x is always higher than g of x. Then the area underneath here is going to be bigger than the area underneath G, right? So the blue area is going to be bigger than the red area. And of course, that looks like it makes sense. We don't have to go through the proof, and it looks like it's going to make sense. Finally, the last rule, if my function is always bigger than a number, okay? If my function is always bigger than the number, then of course the area of this box is going to be smaller than the area underneath the curve. So the integral is going to be bigger than the box. All right, makes sense because it's always high. Now, if I look at the maximum value, so if my function is under some maximum value, then the area underneath this maximum value, so this maximum box over here, is always going to be bigger than the area, the integral of my function. But once again, that look kind of obvious. And if you're curious, you can always look at the actual proof in the textbook. It's not really required. Okay, now that we talk a lot about that, we'll show you what kind of questions we're going to get. These ones, the comparison properties, it's harder to test you right now on this, but we'll use this later on for some of our proofs and when we deal with the conversions of series, I think. For now, we can ask you for a concept like this really quickly. You'll notice it's the same function, and we're playing around with the limit 0 to 10, 0 to 8, 8 to 10. Naturally, 0 to 8 plus 8 to 10 is going to give us 0 to 10. So we're going to write out the 3 integrals like that. First one with the limits from 0 to 8. Second one from the limit 8 to 10. We add these together. The area is going to be from 0 to 10. Substituting the value 12 and 17, we find that the last little bit has to be equal to 5.